Today, we're tackling a problem where we need to transform an array by summing adjacent elements. The twist? This array is circular, and the direction of our sum depends on a given integer k. Let's dive in. Given an array code and an integer k, we need to replace each element in code with the sum of k adjacent elements. If k is positive, we sum the next k elements. If k is negative, we sum the previous k elements. If k is 0, all elements become 0. Remember, the array is circular, meaning the last element is followed by the first and vice versa. A straightforward approach would be to iterate through each element of the array. For each element, we then iterate k times, either forwards or backwards, to calculate its sum. We handle the circularity using the modulo operator. This works, but it's inefficient. For every element, we perform k additions, leading to a time complexity of O n multiplied by k. While space complexity is big O of n for the result array, the repeated summation for overlapping windows suggests a better way. The key insight here is using a sliding window. Notice that when we move from calculating the sum for index I to index I plus 1, most of the elements in our window remain the same. We only need to subtract the element leaving the window and add the new element entering it. This turns repeated full summations into constant time updates. We'll pre-calculate the first window sum, then iterate, updating the sum by subtracting the oldest element and adding the newest element using modulo for circularity. We need to handle positive and negative k separately, as the oldest and newest elements shift direction. Let's trace this with code, as 5, 7, 1, 4, and k as 3. Since k is positive, we sum the next 3 elements. For the first element at index 0, the initial window includes 7, 1, and 4. Their sum is 12. So, the result at index 0 is 12. Now, to calculate the sum for index 1, we slide the window. We subtract the element leaving the window, which is 7, and add the new element entering the window. Since it's circular, the element after 4 is 5. So, the new sum is 12 minus 7 plus 5, which is 10. This becomes the result for index 1. We continue this process, updating the sum for each subsequent position by removing the element at the window's start and adding the element at its end, always respecting circularity. After applying the sliding window technique, our final result array is 12, 10, 16, 13. Each element correctly represents the sum of its next 3 circular neighbors, demonstrating the efficiency of our approach. You'll spot this sliding window pattern when you need to calculate sums or other aggregates over a fixed-size contiguous subarray, especially if you're iterating through the array. The other clear signal is when a brute force approach involves redundant calculations on overlapping segments. The time complexity is big O of n, as we iterate through the array only a constant number of times. Space complexity is big O of n to store the result array. This problem is a great example of optimizing a brute force approach using a sliding window. Try the next problem to reinforce this pattern. Don't forget to like and subscribe for more DSA insights.